could create a graph of our popcorn kernels popping. As time passes, in the beginning, nothing's happening. Then we get one pop, a few more start to pop. In the middle, it's a flurry of activity as they all start popping. And then at the end, we have a few of the stragglers who finally pop. We could also create a graph of students arriving to class. In the beginning, we have a few that show up early. The bulk of them show up right around the bell, and then we have the few stragglers who roll in late. We can also create a graph for the weights of babies, the heights of students who are a certain age, or the time it takes them to complete an assignment. And the same phenomenon continuously happens. You're going to have some people in the low end, some people in the high end, and the majority of people are going to be in the middle. If you were to create a bar graph or a histogram indicating how many people show up at each of those data intervals, and then join the tops of those points to create a frequency polygon, you're going to notice that we continually get the shape of a bell. So normal distribution, which is what we're going to look at today, is also called the bell curve, where we have some data in the low end, some data in the high end, but the majority of data in the middle. In order for this to happen, where we get that shape of the bell curve, we have to have a large enough sample size that it's going to approximate that bell. That's our mathematical ideal, and it tends to happen with living things in terms of height, weight, etc. A few things you need to notice about the bell curve. So one is that this total area underneath is all of your data. Our mean is in the middle, and 50% of our data is therefore below the mean, 50% of our data is above the mean. You're going to notice it never touches at the end, because in theory, we could have a data value that is over here, or we could have a data value that is over here. It's going to extend to infinity and never actually touch that horizontal line on the bottom. It's also symmetrical. So if you were to fold your graph on that line that is the mean, you're going to have the same amount on the right side as you would have on the left side. And this mean and median, if your data is normally distributed, are going to be close. The mode sometimes is going to be within that range too, but the mode is a little bit trickier. The mean and the median for data that is normally distributed will be fairly close together. In terms of the graphs, you want to remember that the y-axis always represents the frequency, the number of items that have that particular data value. In terms of the mean, I'm going to start with this one. We can see that the blue graph has a mean down here. The red graph has a mean up here. If these are two classes, and I'm going to use marks just because you're so familiar with it, we can see that the class represented by the red graph has a higher class average than the class represented by the blue graph. The spread of the data is the same, it's just where they lie on that graph is different. So the mean is going to determine the position that you are at on the x-axis, and the standard deviation is going to control the spread of data. So we can see if these are two classes, they're very similar in the amount of students who have low marks compared to high marks. Whereas over here, we have the same mean. So both of these classes have the same class average, but we can see on the red class, all the students are fairly close together, whereas on the blue class, we have a lot wider spread. So it's the standard deviation that controls that spread of data. So I want you to predict which of these classes here, the blue or the red, is going to have the smaller standard deviation. Because the lower the standard deviation, the more consistent you are. This red graph has a smaller standard deviation. Everyone is really close together. The larger the spread, the higher the standard deviation. So every time we have a situation and they tell us that our data is normally distributed, we know it produces that shape of a bell curve. So we're always going to draw an x-axis, and then we're going to make sure that we never touch on either end. This graph kind of looks like it does, but it actually doesn't. We're going to draw as close as we can a symmetrical bell curve, and then right in the center, we are going to put our mean. So remember, this is our mu, that represents the mean. And then evenly as possible, we're going to try to break each side into thirds. So we're going to draw vertical lines 1, 2, 3 on the right, and vertical lines 1, 2, 3 on the left. This is our sigma right here. So this is going to be one standard deviation above the mean, this is going to be 1 standard deviation below the mean. 2 standard deviations above the mean, 2 standard deviations below the mean, 3 standard deviations above, and 3 standard deviations below. And then there could, in theory, be some data points that are higher or lower than 3 standard deviations, which is why we don't actually touch. Now, if we have enough items or people in the sample size, we know that mathematically we're going to have 34% within this section, and because the graph is symmetrical, we're also going to have 34% in this section. 68% of our data is going to lie within 1 standard deviation of that mean. We know that 13.5% of the population will lie here, which means 13.5% of the population will lie there. 13.5 plus 13.5 is 27. We add that to 68 and we have 95. So 95% of the population is going to be represented within 2 standard deviations of the mean. And then we have, therefore, 5% of the data left. So I know that there's 2.5% down here and there's 2.5% down here. If we break that up, 2.35% are in this range, 2.35% are in this range, which mathematically leaves us with 0.3%. Split that in half equally, and that gives us 0.15% here and 0.15% here. You do not need to memorize those percentages. This is going to be on your formula sheet. Those are the standard percentages every time our data is normally distributed. And if we know that, we can make a prediction how likely is an event to occur based on what we know about that bell curve. Our first question, it tells us that Jim is raising Siberian Husky dogs and the data of their weights is normally distributed. As soon as you see that it's normally distributed, you know you need to draw a bell curve. It's not always going to tell you draw a bell curve, but you know that's what you need to do to solve the problem. The mean that they give us is 52.5 pounds. So we're going to go, now when you draw this, make sure you do not touch at either end and try to get it as symmetrical as possible. And then we're going to go in the middle and we're going to draw a vertical line going straight up and down. And we're going to put that mean in there, 52.5. And then I'm going to get you to box it just because we want that to stand out from the rest of our data. And now we're going to go 1, 2, 3 standard deviations above the mean and 1, 2, 3 standard deviations below the mean and try to make sure that the width of each of those intervals is the same. Now, you know using your calculator from the previous lesson how to find that mean and standard deviation. In this case, it's given to you. So it tells us our standard deviation is 2.4 pounds. So because this is 1 standard deviation above the mean, go get your calculator and you're going to type in your calculator 52.5 and then we're going to add on that plus 2.4. And when you type that in there, you're going to get 54.9. And then again, plus 2.4, and we're going to get 57.3. And one more time, plus 2.4, and you're going to get 59.7. Now, I always do that end first, doesn't really matter. Now we're going to do below the mean. So we're going to clear your calculator, and we're going to start again. So enter that 52.5, and this time we're going to go minus 2.4, and we're going to get 50.1. Minus 2.4, and we're going to get 47.7, minus 2.4, and we're going to get 45.3. Now, if you take a look at your formula sheet, we know 34% of the data lies within there, which means 34% of the data lies within there. We know this is 13.5% of the data. We know this side is 13.5% of the data. We also know that this section here is 2.5%. Specifically broken down, this here is 2.35%, which leaves us with that 0.15% later. And that may not be on your formula sheet, but you can calculate that, knowing that 100% of the data has to lie underneath that curve. And then because it's symmetrical, we have those same values over on that side. And now we're set to answer any question. So in the first question, we're looking for what percent of dogs could we expect to have a weight between these two data values. Now, you need to pay attention to, are we above, are we below, or are we between? So in this case, we're between. So you might even want to grab a highlighter or something and block off that range. So I can see that 47.7, that's right there. 54.9, that's right there. So that's perfect. It lies right on those standard deviations. So I'm going to take all of my data between there and between there, which means I'm specifically looking at this range. And then we always kind of want to shade on the graph, where are we looking at? So I can see now that I'm going to add up that 13.5% plus the 34% plus the 34%. And when I add those together, that's going to give me my 81.5%. I would expect 81.5% of the dogs to be within those two weight ranges. And take a look at the curve. You can see that is the bulk of the area, so that makes sense. In the next one, we're now looking for the percentage of dogs we would expect to be within these two weights. So again, I look, that's right on the standard deviation, so that's good. And we're going to block off that area, shade that in, and then we're going to add up those percentages, and this is the percent of dogs we would expect within that weight range. I want you to pause the video and you try the next one. Now this time we're looking for the percent of dogs we would expect to be less than 45.3. So take a look at your graph and what do you think? First, find 43.5 pounds on your bell curve. So there it is right there. And we want to be below that. So we're going to shade everything below, which in this case just happens to be the one section. So 0.15% of dogs would be less than that weight. If you're given a question like this, where you're provided a bunch of data points, in this case, the data represents the longevity of a cell phone lasting in years. First thing we need to do if we're asked about normal distribution is we need to calculate the mean and the standard deviation. You know how to do that from the previous lesson. So you would enter all of these data values into list one and choose that one variable statistics to get those statistical measures. Now I did this for us just to speed things up here. So I calculated my mean, I calculated my standard deviation, and I also pulled the median from that list of data. Now we do need to know whether or not this data approximates normal distribution, because if it doesn't, we can't use those percentages on the bell curve to make any kind of a prediction, which is what she wants to do. So we always have to see, is this going to be normally distributed? If not, that whole bell curve doesn't apply. So there's a couple things you want to look for. Are the mean and the median close? So you can see that the mean and the median in this case are fairly close together. And then the best thing to look at is the shape of the graph. So if I were to plot these points, I went through and found this is my lowest value, this is my highest value out of those 50 data values that I'm given. So I kind of just made a graph here. Now you would have to keep going, but this is 1.1. I've got two phones that lasted 1.7 years, one phone that lasted 1.8 years, two that lasted 1.9. And if we were to keep going, we can see that it is going to form that shape of the bell curve. And the other thing you could do is check. Knowing that 68% of our data is within one standard deviation, and knowing what that standard deviation is, you can count out of those 50 values, how many of them would fall within that range. Is it close to 60%? I accidentally wrote the wrong mean down, so just switch those numbers back around. So just to show you how we could calculate this, if I put the mean here and add the standard deviation to it and subtract the standard deviation from it, I know 68% of my data values should be within that range between 2.004 and 3.008. So I just went through, out of the 50 values in the table, I just checked off all of the values that would fit within there and then calculated the percentage to be 70. I know 68% of the data is within that range, so 70 is pretty close, indicating it probably is normally distributed. I would also then continue on with 2 and 3 standard deviations. Once we've established that the data is normally distributed, you know to always draw a bell curve. Box off the mean in the middle, and then we're going to add 1 standard deviation, 2 standard deviations, 3 standard deviations. So in your calculator, you're going to enter that number, and then you're going to go plus 0.482, plus 0.482, plus 0.482. Clear your calculator, enter the mean again, minus 0.482, minus 0.482, minus 0.482. Look at your formula sheet, and we can fill in those percentages. Now, in this case, we're looking for what is the chance that Shirley's phone is going to last more than 3 years. So this is the closest deviation we have to 3 years. So if I want to last over that, I'm looking at these 3 sections on the graph. I know these two together add up to 2.5. So I'm going to add that to 13.5. And there is about a 16% chance that her phone will last over 3 years. Now I want you to do the last one. So similar to the previous one, but this time we're looking for what is the likelihood it will last at least 18 months. And pay attention to your units. These are the number of years. So the first thing you have to do is to convert that into years. Okay, so we know 18 months is 1.5 years. So the closest deviation I have to that is going to be this one here. Now, my phone has to last at least 18 months. If I choose anything down here, my phone has not yet made it to that 18-month mark. So we want a phone that's going to last over that. So these are the values I'm looking at. And instead of adding them all up, the easiest thing to do for me was just to take 100% of my area and remove the pieces we don't want. I know already this is 2.5, so I subtracted that. And so there is a 97.5% chance that phone is going to last over that 1.5 year mark. You would not want to buy a phone that's going to die right in the beginning. So for every question where we're looking at what is the likelihood or chance of something occurring, if our data is normally distributed, you're always going to draw that bell curve, fill in your percentages, and then get the information from that graph.